Welcome to I Can Act the Youth Talks. It's a great pleasure to meet all of you online, every Thursday and Friday, every Tuesday and Friday. This Tuesday event is so excited for the young scientists really shaping the future as a world. This is Alice Zhang from Peking University. Warm welcome from Beijing. And today I'm here, to give you a brief introduction for ICANX and what going next year. So ICANX actually a lot of people know this, follow us since 2020 and the very beginning of COVID-19. That time we start this talks online. We invited the top scientists from the whole world jump in to deliver the very latest result of their work. We think that we use this science and technology to connect world and the universe. So this X meanings, everything. This X also meanings of questions and the uncertainty and the challenges we facing. We deal with it and we solve the problem. We're moving forward. So yeah, that's how and why I can X come out. We're really proud of that. We got so many speakers and so many top speakers, online, and all this technology and the science from their groups were popular and educated, many people. So in since 2020, uh 20, April 17th, the first, week, we have these talks, and till last week, we have more than 165, weeks. Many speakers from 5 continentals and 84 countries, and almost 1,000 speakers on this line. And we have the maximum, audience on 1 week is over, 500,000. Until now, we're really proud of that. We 60, millions, online, audience. Yeah, it's really a very popular program. And then we have all these speakers, we're so proud of them because they from all of the each, in many fields and wonderful jobs and wonderful and almost everyone think they have a given the very exciting talk on ICANX. So we have a sorry, yeah, we also have a ICANX club in Beijing. So this club has a lot of kind of fun. Also can give lectures, workshop and discussions and all these exhibitions and even fun outdoor event. So it's a very exciting, place for the ICANX family members jump in and to go together. So this was an event we not only for the scientists now, we also for the future scientists, tomorrow scientists. So we host the event in the weekend for young kids to learn, and to show the demonstration of the technology and what for the future. So we're really proud of that. We're nursing the future scientist in ICANN X. And this was our proud, because we have every year, every Friday we have this ICANN X talks. Invited the super speakers. We also have an organizer team from the whole world, each continent. So yeah, we have the helpers from place. And this year we also have this kind of youth talks. Really proud of that. The youth talks. Since February 14, we have continue every Tuesday. We got the young scientist to host this event. This Tuesday event, they invited two or three, young scientists from different place for the talks online. It's welcome, and it's really a popular, talks. I can act proud of these young scientists and all of them. And this year we have the big pictures. We almost there. We have a dream to have 100 countries, 1,000 scientists, and over 100 million audience. We almost year. Yeah, so we think, we make the big dream for a year of science around the world. Close, yeah, to this dream, to this target. A lot of people are asking me, Alice, what are you going to do next year? This year, you know that, yeah, this third year I can X already, so exciting. What are you going to do next year for I can X? Yeah, that's I'm going to tell you. We have a even more exciting event for next year. We have not only for I can X online, this weekly talk, for you, and the Tuesday for the senior scientists on Friday. Next year and 2024, we're going to have, the event for on-site, so people to meet in person. So this big plan is will come out and the July 11 to 12 and Davos, Switzerland. That was is famous, for the every year they hold the economic summit. That's the influence all over the world. So next year in the summer, July, yeah, you will have another big event, and the Davos will be the next, summit, all over the world. The influence of the world is I can access summit. Yeah, so this is will be the best place for us to then this also will be the best, place and the start for I can apps to, get the people, scientists and all of the world to meet each other to, driving for the future. So, today it's my great pleasure to introduce what we're going to do on this Davos Summit. So on Davos Summit, actually, we will have six kind of keywords. The first is innovation, second is science, technology, investment, management, environmental. Let me explain why all this. Because innovation, everyone knows that this is the most important things, for all of the world. Not only you in your science, technology, you in each field. So we put the first words as innovation as a keyword. So we want to invite the different place have innovation idea, educations, and also, thinking, jumping with us. So science and technology, of course, is I can add the folks. Yeah, we have got the then get the picture for the whole world, scientists and the beautiful technology showing on I can add always. So we invited all these scientists and the future technology players get to Davos to discuss about all this. For sure that if you just have all these academic parts, that will not be enough because we must engage with the market, engage with industry, make everything really benefit. So we will invite the people's investment part and for the manager and also for environmental, sustainable development. So all these peoples, all these industries, all these players, please come to join us. For short, this sixth field. For short is time. I think everyone you come to I can access summit. It's time for you to come to this summit. It's time for us to discuss, what we're going to do, what we can contribute for the future to the whole world. So this will be our focus, on Davos next year. So now you know that if you are, in this related field, you are welcome, and you are welcome to join us. And this was the plenary speakers we already confirmed. So Professor John Mayer Lee and was a Nobel laureate. He also the best, educators nation, and we learn more from him. And Jack Lish was the president of Australian Academy. He also was a premier, so I can add some moderators. It helped me from the very beginning. I can add the platform. Really proud of him, to be the president of Australian Academy. Also have a lot to share with us for science and technology for the futures. Professor Saifur Rahman was a president and CEO So he leading the largest, academic society. Also have most here with John Rogers, the most famous scientist, also the first speaker on ICANX. Peter Size, uh, co-president of academy. So he is also the best teacher for you. All know that he really a lot for innovation, education, and also investment for the technology startups. So we have a Chattanooga, we have a Dubious, we have Annie, we have a Professor John. This was plenary speakers. Now we will have more, plenary speakers and some super stars to coming in and to jump in. So yeah, I thought that this will be very exciting. You will be exciting to jump in with us and to get to the department. More things is for the schedule. We'll have 2 days a year. Of course, you can imagine how tight it is. We'll have a very tight and exciting, the event. More things I'm going to tell you is not only we talk about each time the technology, innovation, all the hard topic, we also will have some, fun because we invite a scientist bond, rock and roll, in the sun with science. All scientists was a player. That will be more fun, to have a world ceremony, dreaming to have all these exciting things on this, exciting event. Another thing, the venue. This was the Davos, the venue, the best venue for the conference summit. Yeah, if and always the place always the most well organized, and we will have some special arrangement and for startups and show exhibitions once for. And yeah, we will announce a few words on big summit. Of course, our ICANN, the Young Scientist Awards, our Innovation Awards, ICANN, our ICANN Startup. So today is the Young Scientist Party that introduced the Young Scientist Award. Else. This ICANN, the Young Scientist Award, actually this for online since ICANN at the very beginning. So next year we will have it on site. So all the independent young scientists who obtained the PhD after, June 1st and the 2013th, can send their, information to apply for apply this next next year. The deadline is next June, June, okay, next January. Okay, yeah. So that's a requirement. Here, let me highlight this. What's the most important thing? Independent science is a brief outlook of also service, education, and outreach. Okay, these three parts will be the most important parts of how we evaluate young scientists work. So if you are qualified, please do remember that submit information and your materials to our email and to the January January 1. Yeah. So this is application. We also need to recommend there. Yeah, send the recommendation letters. So all this will be done next week. After that, we will screening all these materials. We'll have the online, selection first. Then we have the final defense and doubles. Yeah, we'll have the fun for award ceremony. As I say, that will be a big highlight. Do believe me, we'll make that much more fun. And to make this, young scientists more exciting, and we want to scientists who jump in us with ICANX Young Scientist Committee. So the co-chair will be Professor Martin and Professor Huang Qian from China and one from US. So the volunteers for this Young Scientist Committee, if you willing to contribute, promote the young scientist works and evaluate the application materials and organize a final event. All this, if guaranteed to do something work, please, contact us. Now, deadline for this committee is October 7th. So, to remember sending material and sending message to Professor Martin and Professor Huang. And this was all well hosted by the ICAS Association. And so, this will also will be our best, the first ceremony person of ICAS big family. So I hope everyone we met next year at ICAS Summit Davos. All big parties will have a summit. So that's for you and for all of us. So looking forward to that. I can add as a keywords as a changing. Okay, welcome all of you. Now, my time is over. We will continue to today's young scientist, talks. So let's welcome Professor Xiaoqing from Ireland to be the moderator of today. So, Xiaodu, are you ready? Dr. Du, ready the floor, please.
Yeah, thanks, Alice. Thanks so much for your introduction. And I'm going to share my slides. Okay. Okay, welcome everyone. Welcome to ICANX talk. And today we have three speakers. And we have three speakers. And our topic is MXene-based energy storage process and device. So the first speaker is Xuehang Wang from TU Delft. She will give a talk which is related to the supercapacitors by using the MXene-based material. And also we will have the talk by Christopher Shuck, and she comes from Rutgers University, and she will give a talk of understanding of chemistry and structures. Also, the last one is Shayan Seyedin, and she comes from Newcastle University. Okay, first I will introduce Xuehang Wang, and I will first introduce Xuehang Wang, and she will give a talk. Okay. Xuehang Wang is an assistant professor at the Department of Radiation Science and Technology, TU Delft. She obtained her PhD degree from the Norwegian University of Science and Technology and was a postdoc researcher at Drexel University, mentored by Professor Yuri Gogosti. Since 2015, she has published more than 30 peer-reviewed papers with an H-index of 20. She has also won several personal team awards, including EFRC Team Science Award, Costa Award Postdoc Fellowship, and RSC Horizon Prize. Her research interests includes mechanistic study on high-performance electrochemical energy storage process, synthesis of normal nanomaterials, especially transition metal carbides, carbides, MXenes, for battery and supercapacitors, and the interfacial engineering at the electrolyte interface. Okay, Xuehang, please share your slides and you can start.
Xuehang, you mute yourself.
Okay, yes. Yeah, hopefully now it's okay. Yeah, thank you, Xiaocheng, for your kind introduction, and also many thanks to ICANX. I'm very glad to deliver a talk here on the charge storage mechanism of MXene-based pseudocapacitor. Yeah, firstly, some background information about where my department is. And so I work at TU Delft in the Radiation Science and Technology department. So our university, TU Delft, locates in between the Hague and Rotterdam, and also very close to the Amsterdam. So yeah. So we our department locates on the campus of TU Delft, and there are a neutron reactor in our department. So with these neutron reactors, we have several beamline. Specifically for the neutron diffraction, like small angle neutron scattering, as well as the neutron depth profiling are the most relevant techniques that are used to review the chemical structure and also the battery behaviors in situ. So our program related to the reactor is called Oyster. So welcome to have a collaborations on the neutron reactors beamlines. So some information about our group. So I work in the group called Storage of Electrochemical Energy. So we are a very large group containing about 5 PIs and 40-ish scientists and PhD and postdocs. So our group is very good at designing in-situ cells for various characterizations, including solid-state NMR, solid-state in-situ XRD. Okay. Yeah. So let's move to the topic today. So for the electrical energy storage, we always want to have higher energy and higher power density. That is because we want to have our cells to be charged faster, as well as we want our cells to be used for longer time before recharge. So this is why obtaining a simultaneous high energy and high power is very essential for an electrochemical energy storage devices. There are typically there are two general type of energy storage devices: batteries and supercapacitors. So compared to the batteries, the supercapacitors have relatively lower energy density while relatively higher power density. Meanwhile, supercapacitor is also have a relatively long cycling life, a very good safety, and also it's because of its higher power density, so it's capable of faster charging and recharging. The problem with the supercapacitor is a relatively low energy density. So in order to increase the energy density of a supercapacitor, we can expand the voltage window, and we can also increase the capacitance. However, still so far for the electrical double layer capacitor, the capacitance and as well as the energy density is still not as high compared to the batteries. So in order to further improve the energy density of a supercapacitor, then we can introduce pseudocapacitance. Then you will ask, what is pseudocapacitive charge storage? So both double layer capacitor and the pseudocapacitor belong to supercapacitors. However, compared to the double layer capacitor, which is dominated by the physical absorption-desorption of ions, the pseudocapacitive charge storage mechanism involves the surface redox activity. So it means that the intercalated ion will react with the surface of the material and contributes to some partial electron Faradic processes. However, if we compare Faradic processes in a pseudocapacitor and a battery, the pseudocapacitive charge storage is mostly on the surface. So it means the process is surface controlled, while in a battery, the process or the Faradic processes is mostly diffusion controlled. So in this way, a supercapacitor can realize much faster energy storage rate compared to battery, Meanwhile, it can also store more charge compared to the double layer capacitor. So MXene is like an emerging family of 2D material, and it shows very promising properties for various different applications. So today I'm just showing the applications of MXene as a pseudocapacitor. So what is MXene? MXene is a transition metal carbide or nitride, 2D transition metal carbide nitride. So here it shows like a schematic of a typical M3C2 structure of MXene. So basically it has 3 layers of metal and 2 layers of carbon or nitrogen. Then they interleaved with each other and forms 1 layer of MXene. And on the surface of MXene, it's fully covered by different functional groups, including oxygen, OH, chlorine, and fluorine. So with this structure, then we will have a conductive carbide core, which ensure many MXene have a very good electrical conductivity. While because the surface is fully covered by different functional groups, then it's like mostly surface redox active. Besides this 3-2 structure, so we also have 2-1, 3-2, 4-3, and 5-4 structure. And besides this single metal structure, we also have double metal and also high entropy MXene with more than 4 different metal species in the metal layer. So here are some SEM images of the MXene. So here it shows like the layered structure of like the stacked MXene flakes, as well as this cross-sectional images of MXene electrode. So you will see that MXene electrode is stacked by multiple hundreds or 1,000 layers of MXene flakes. And here it shows the MXene coated on a substrate. So it's a very large surface area. And now so it have already been realized that MXene can be produced by like a kilogram of productions in the lab. So the mass production of MXene is also on the way. So for why MXene is a promising choice for energy storage. Here I summarized several points that makes MXene very attractive. So firstly, of course, it's because it's have like a very tunable and like surface chemistry. So it also have like various electronic properties. And the surface chemistry allow it to have like a faster surface redox reaction. And the surface area is relatively large. And this MXene also have a high metallic conductivity. So this is a major advantage of MXene because then it will minimize the self-discharge. It will also be very suitable for low temperature operations. And MXene, because of the high conductivity, it can also be used for current collectors and binders. And because of the MXene have a very flexible interlayer space, so various ions can intercalate MXene, so from as small as proton and as large as ionic liquid ions. And MXene can form freestanding film, and it have tunable flake size. And very interestingly, MXene, because it can form closed solution in water and in various organic solvents, so it can be painted, written, and printed on various substrate, which is very easy to make devices, which later I think Shayan will mention about MXene related devices. So talking about the mechanism, so MXene shows a very good pseudocapacitive performance in the acidic electrolyte. So here it shows a schematic of like MXene in like sulfuric acid electrolyte. So the proton in the electrolyte will intercalate into the MXene interlayers, and then this proton will interact with the surface of MXene and have a partial electron transfer with the MXene surface. And in this way, there will be some surface redox reaction occurs, which contributes to the pseudocapacitance. So here it shows the cyclic temperature of a thermogram of MXene in the sulfuric acid electrolyte. So by further make the MXene into a macro porous structure, MXene have an extremely good heat capability. So with microporous structure in acidic electrolyte, the MXene is able to maintain 60% of its initial capacitance at a scan rate up to 100 volt per second, which is really very much higher compared to all the other materials. However, the problem with the acidic electrolyte is that it's acidic. So it's corrosive, as well as if we are using the aqueous electrolyte, then our voltage window is relatively narrow. So it means that the energy density is also a little bit limited. So in order to extend the voltage window of MXene, then here in this work, we try to cover the MXene with polyaniline. So what we do is that we first synthesize a macroporous MXene. So in this way, the MXene have a more exposed surface area. And then we use deep coating. We coat the polyaniline on the macroporous MXene, and then we compress the electrode into a compact electrode. Then in this way, polyaniline kind of wrap all the active surface of MXene, which can protect the MXene from oxidation. So what we do is that we further cycle the electrode in the acidic electrolyte. We find that the voltage of MXene extended from 0.2 to about 0.55 volt versus silver superchloride in the acidic electrolyte. So in this way, we are able to pair this electrode with pure MXene as the negative electrode. Then we are able to achieve about 1.2 volts for the full cell. And with this full cell, because of the high capacitance of the single electrode as well as the high rate capability of the single electrodes, so we are able to achieve a very high energy density in the aqueous electrolyte and also extremely good power density. However, still we are using the acidic electrolyte. So if we see the acidic electrolyte so here is the X-ray near-edge spectroscope. So what we can see is that the KH of the titanium KH will shift during the charge and discharge process. So it means that if we charge MXene from like 0.3 volt to negative 0.4 volt, there will be the energy will shift to lower energy, and it corresponds to a reduction process. And like vice versa. So during the discharge process, there will be the MXene electrode will occur. Oxidation process will occur. So this process is pretty reversible. And during the process, it's we observed some partial electron transfer, which is confirmed by this X-ray absorption. However, compared to the acidic electrolyte in the neutral aqueous electrolyte, the KH energy shift is much minor compared to in the acidic electrolyte. So it means that the pseudocapacitance is relatively minor compared to the acidic electrolyte. And the question will be, if we want to use like a non-acidic electrolyte, then how can we increase the pseudocapacitance of MXene in like the non-acidic electrolyte? So in this work, we find that by using different organic solvents, the capacitance can be like doubled compared to the other different type of organic solvents. So here in the propylene carbonate electrolyte, the charge storage capacity reaches 470 coulomb per gram, which is almost 2 times compared to acetonitrile and the DMSO system. So in order to understand why in the propylene carbonate system, it's dramatically different from the other 2 systems, so we have performed in situ XRD. And so here, so in the DMSO system, the interior space is about 19 Armstrong. And in acetonitrile, the interior space is 13 Armstrong. And in the propylene carbonate, the interior space is only 10.7 Armstrong, and the interior space doesn't change during the charge and discharge process. So in order to further reveal like what is actually happened during the charge and discharge process that leads to this interlayer space, we further perform the molecular dynamic simulation. So what we can see that because of the large interlayer space, so there are 2 layers of solvents allowed in between the MXene interlayers. So then, because in these 2 layers, the dimethyl sulfoxide, like the methyl groups, points away from the surface, and then it formed like these hydrophobic environments, which allow the fast integration of lithium. So in this way, in dimethyl sulfoxide, the kinetics is much better. And however, in the acetonitrile system, only 1 layer of a solvent is allowed. So actually, the solvent will block the way for the lithium depletion, which also introduce like a dramatically much larger resistance compared to the dimethyl sulfoxide system. While in the propylene carbonate system, because there are no solvents in between, so the lithium can just intercalate, fully dissolvated, and then they are able to be compact with each other. So in this way, the charge storage capacity is much, much higher than the other 2 systems. So with the propylene carbonate system, we further perform the read capability and also the long cycling life test. So we get like very good read capability as well as 94% of capacity retention after 10,000 cycles, which claims that by properly choosing the proper solvents or proper electrolyte, we are able to achieve high energy and high power with the compatible electrolyte. So far we have mentioned that MXene's operation in acidic electrolyte, in the organic electrolyte. However, there are 1 zone that has never been achieved. This is the positive electrode, positive potential. So by using voltage salt electrolyte, we find that we are able to extend the potential from about 0 volt to 0.8 to 0.9 volt versus the silver wire. Meanwhile, with the extension of the potential window, we also observe an additional electrochemical energy storage processes that emerges at the positive potential. In order to understand these processes, we have firstly performed the in-situ XRD. So because this process occurs at the potential more positive compared to the open circle voltage, so we first assume that this process is correlated with the anion depletion. However, the in-situ XRD gives the opposite suggestion. So at these black points, where if it's anion depletion, it corresponds to a intercalation like interlayer space expansion. However, we observed a dramatic interlayer space shrinkage. While at these red points, it should be like interlayer space decrease. However, here we observe interlayer space increase. So it means that instead of anion integration, deintegration, this process is actually correlated with the cation depletion, deintegration. To further confirm it, we performed the in-situ XRD again in using lithium TFSI, because TFSI has a much larger size to chloride ions. So if it's anion depletion, then the interlayer space change should be more significant compared to chloride ions. However, here the level of interlayer space change is similar. So again, it supports that this process occur at positive potential actually is correlated with the cation depletion, deintegration. Then we further perform the in situ EQCM, electrocold microbalance. So with electrocold microbalance, we are able to divide the processes into 3 stages. Stage 1, here from the most positive potential to this redox set or the onset potential of the peak. There are almost no mass loss during this process. And stage 2 is the peak stage. So at this stage, dramatic loss of the material in the electrode. And stage 3, so there are minor loss of the electrolytes in between the MXene layers. So we further can calculate the number of water that accompanies the lithium depletion processes. So what we find is that during the peak potential, so each lithium intercalation will bring about 3 water molecules. So in the bulk electrolyte, each lithium is accompanied by 3 water. So it means that the lithium intercalation at the peak potential is dissolution free. And at the potential that has no peak, so there is only 1 to 1.2 water accompanied lithium intercalation. So we see this is about partial dissolution of the lithium occurs. So so it's very interesting to see that at different charge stages, so the status of the lithium depletion is significantly different in this water in salt electrolyte. So this phenomena has also been observed in the molecular crowding electrolyte. So molecular crowding electrolyte is one type of new electrolytes that has been developed recently. So by adding those kinds of molecular crowding agent, for example, PEG, into 2 molar lithium TFSI, we are also able to observe these kinds of peaks at the positive potential. And this process contributes to 25% of the capacitance increase. And we find, interestingly, during the charge and discharge process, the PEG 400 or the molecular crowding agent that we added into the system also co-intercalate with the lithium in during the process. And this leads to about 5 Armstrong of interlayer space change during the charge and discharge process, which is the largest reported value for the MXene electrode so far. Okay, then we mentioned about the neutral aqueous electrolyte and also MXene in water in salt electrolyte. However, at the negative potential, so usually there are no redox activities observed. So interestingly, we find that if we oxidize MXene, from 0 to 1.2 or 1.3 volts, actually after each oxidation, we find stronger and stronger surface redox reaction at negative potential. And in order to confirm this process is correlated with the surface redox activity, we have performed the in situ X-ray absorption. So it's very clear that this X-ray absorption pattern is very similar. It's different from the titanium oxide and titanium dioxide, which means that the MXene is not fully irreversibly oxidized into TiO2. While during the charge and discharge process, we can observe that oxidation and reduction processes reversibly. And we also first obtained that during the process, 0.08 electron transfer observed per titanium atoms occurs during the process, which corresponds to 104.2 farad per gram. So this is agrees well with the capacitance of the MXene in the water in salt electrolyte. So why a partial oxidation introduces surface redox? So we compare this the X-ray absorption pattern with the one that's without the oxidation. So we find that the valence of titanium in Ti3C2 increases from this 2.43 to 2.86. So in this way, because the valence of MXene become a little bit higher, then it also become easier to be reduced at more positive potential. So this explains why we have observed the interesting surface redox activity by partially oxidized MXene in situ in the electrolyte. Okay, so finally, I would like to thank my many thanks to my previous mentors, also my colleagues, my students, and also many thanks to my collaborators. Of course, ICANX will be a very good database for you to find many interesting talks. But if you're interested in electrochemistry, some tutorial videos about supercapacitors, then please welcome to my YouTube eChem channel. And here are my contact information, and thank you for your attention.
Thank you so much, Xuehang. Thank you so much for your nice talk. And welcome to follow Xuehang's YouTube channel. And welcome to our next speaker. Yeah. Welcome to our next speaker. He is Christopher Shuck, and let me introduce him. Dr. Christoph Shuck is currently an assistant professor of chemistry and chemical biology at Rutgers University, USA. He received his bachelor degree from Princeton University, and he completed his PhD degree from the University of Notre Dame. His research focused on controlling solid-state reactivity by modification and understanding of reactant nanostructures. During his postdoc studies and as a researcher assistant professor, he worked closely with Professor Yuri Gogossi to develop novel MXenes and MXenes. He discovered the first member of the M5AX4 and M5X4TX MXenes, resulting in the definition of both materials being changed. He also focused on the scalability of MXene synthesis, demonstrating kilogram batch size of 2D materials. He also collaborated with a variety of scientists to apply MXenes, including the energy storage, magnetic interference shielding by medicine catalysis, and something like this. He has published over 18 scientific publications, in addition to 2 book chapters. He has been cited over 5,000 times and currently has a H index of 32. Let's welcome our speaker, Christopher. Yeah, please share your slides and you can start.
Wonderful. Thank you so much for that wonderful introduction. I'm very honored to be giving a talk at IconX. And thank you for the organizers. And I want to say I was very impressed by Xuehang's talk. That was absolutely wonderful. I feel like I learned so much about MXene electrochemistry. So thank you so much. So what I'm going to talk about today is a little bit different than what Xuehang and Shayan are going to talk about. So in general, with MXenes, there's a huge amount of chemical variability that we get to play with. And this gives us a tremendous ability to tune MXene properties to essentially choose or tailor the best MXene to what we want rather than using what's available. So you're going to hear today about a number of different applications of MXenes. Both Xuehang and Shayan do a lot of electrochemical energy storage, but MXenes are used in a large variety of other applications as well, including as catalysts with oxidative dehydrogenation, for example, using them for additives to polymer composites to make either multifunctional materials or as strengthening additives themselves. They've received a lot of attention for EMI shielding, as they can outperform nearly any other material of the same thickness. You can use them as single MXene layer thick gas sensors to discriminate between different mixtures of gases with ppb level accuracy. You can use them as spray-on optoelectronics for flexible devices or electronics that you can easily make. We've recently been doing a lot of stuff with anti-cancer and antimicrobial activities. I'm not going to focus on this, but some MXenes actually do deactivate COVID even. So there's a absolutely huge host of applications that MXenes fulfill. And you can imagine, if you look at this huge variety of applications, it's impossible that one MXene is going to be the best for all of them. So it's important that we understand exactly how you can make the best MXene for whichever application. So generally with MXenes, because they are produced from this ceramic max phase precursor or occasionally a similarly structured max phase or non-max phase precursor, This lets us essentially choose the properties when we're doing solid state synthesis. So if you look at my rotating M3AX2 structure, we have generally 3 easy variables that we can see, and then a few invisible variables we can tailor. We can imagine changing these metallic M elements. So within max phases, this follows a huge number of chemistries: titanium, vanadium, niobium, so on and so on. You can change the X site chemistries themselves. So this could be carbon and or nitrogen, or recently we've seen a few other elements incorporated. With the max phases, you could change what the A elements are, so what these red layers are. Typically for MXene synthesis, we keep these as aluminum because it's the easiest to produce MXenes from, but we've also seen silicon or gallium be used. From there, whenever you etch your materials, whether you're using pure HF, in situ HF, molten salt, alkali, or any of the new approaches that have been developed, you will be left with a multi-layer MXene, which has our surface groups on them that you can essentially tailor them by changing how you're etching them. So this is another variable that leads to differences in properties. And then however you delaminate them, again, allows us to tailor the properties. If you use inorganic intercalants to delaminate versus organic intercalants versus solvents or sonication, all of these lead to different properties. And understanding how all of these variables fit together gives us a lot of insight in how we can tailor and control properties. Now, I don't have time to go over every one of these factors today, but I published this article earlier this year that I recommend you check out if you're interested. There's a number of effects that even Xuehang has mentioned earlier today about the different solvents or what happens if you oxidize your MXenes a little bit. All of these variables play a part, and this article is kind of a brief overview of what each of these variables are and how you can control them beyond what I'm going to focus on today. So what I want to draw your attention to with MXenes is each different MXene chemistry has starkly different properties. So I'm going to focus now just on colors of MXenes, but I want you to imagine that the optical properties are the most easy to see because it's optical, right? But along with the optical properties changing, you're changing the electronic properties, you're changing the mechanical properties, you're changing the chemical properties. And this leads to differences in every single application space and every single field. So if you just take Ti2C and switch it to Ti3C2, so you add one more layer of titanium and carbon, you get a completely different reflectivity. So you get a green reflectivity to a purple, or a wine-colored transparent colloidal color versus green. And you can quantitatively see what this looks like over here. So Ti3C2 is this characteristic plasmon resonance around 780, whereas Ti2C is over here at 550. And switching titanium to niobium gives you another large difference. You get green to gold instead, or a nice blue colloidal color. And you can go through the same with all of these as well. So you can very quickly see that each MXene has properties that depend so much on what the actual chemistry is. And understanding this and controlling this gives us an unparalleled amount of tunability to choose MXene properties that we actually want. Now, I do want to mention before I continue that all MXenes are scalable in their synthesis. And this is because we're doing a top-down synthesis approach instead of a bottom-up synthesis approach. So with one of my colleagues, Mike Shakarev, we produced 1 kilo of MXene in less than 1 day, and we were able to delaminate it within a week. So Xuehang showed you a lot of supercapacitors and electrochemical energy storage. This batch we produced in 1 day in a lab can make 5 million printed supercapacitors, where you can cover huge swaths of area with a 45 dB EMI shield. Or for Shayan, I put a textile EMI shield as well. So this gives us a lot of very unique ability to produce materials and produce stuff that is useful on a more than laboratory scale. So let's just briefly talk about max phases. So this figure is even out of date, but with max phases, we have this large amount of chemistries available for the M site. So I'm going to focus primarily just on M site today. We could spend days talking about changing each of these variables and what this leads to, but there's a couple things you can do with max phases. So you can produce them in the single M element one, which is more common. So Ti3AlC2, for example. But because we're producing these from solid state synthesis, and because the max phase chemistry is so flexible, it allows you to actually choose 1, 2, 3, or multiple elements on each of these sites. So I can choose 2M elements, 3M elements, 4. Xuehang showed even the new high entropy stuff that has 5 elements or more in it. You can do the same thing with A site or X site. And then within each of these, you can get different crystal structures themselves. So I showed already how there's a large difference between Ti2C and Ti3C2. And this is going to hold true of all of the different analogs with different structural analogs. So this gives us a tremendous amount of variables that we can play with, and we can actually control to get properties that we target. So what I want to focus on is an interesting class of MXenes called solid solution MXenes. So these ones, this is an interrelated set that we chose where you have titanium, niobium, titanium, vanadium, and niobium, vanadium. So they make this interrelated triangle where we can imagine each of the different points of a triangle is the pure M element max phase or MXene. And we can essentially choose whatever chemistry we want anywhere along this triangle and understand how its properties work. So these structures follow Vegard's law. So it's very easy for us to measure the lattice parameters and understand how the chemistry changes, even just based on how the crystal structure itself changes. And so in addition to using EDS or XPS or whatnot, we can very easily determine exactly what the chemistry we're studying is, rather than assuming based on whatever stoichiometry we put it in. But for simplicity, I'm going to leave the stoichiometries that I put in as the true stoichiometries. The true stoichiometries are off by less than 1% in most cases. So it's a pretty close approximation. Now, if we look at what the colors of these MXenes look like. So I showed you before that Ti2C is this green color and niobium 2C is this gold color. And so in reflectivity, I'm able to essentially choose whichever color in between this I want. Now, my eyes are not spectrophotometers, and so I can't tell you necessarily what wavelength each of these is going to, but you can see that it's shifting, it's gradually shifting in between them. You can see the same thing happen with titanium to vanadium as well. And within niobium and vanadium, if you remember from the graph earlier about the optical properties, both of these are right near the IR. So we can't necessarily see this variation by eye, but you can imagine the same kind of variation is happening with these chemistries as well. And with all of these, just as a quick statement, all of these are phase pure MXenes. So all of the properties I will show you is just pure MXenes. There's no impurities in them. There's no severe oxidation or anything of this sort. And so we checked this with both X-ray diffraction and Raman spectroscopy. And so if you're interested more in this, you can check out this very nice JAX paper. And one thing we were worried about, because there are multiple different kinds of multiple MXene chemistries. In some cases, some of them are ordered structures. And we wanted to be sure that what we're looking at is truly solid solution and there's no local ordering. And so we looked at all of the different MXene chemistries, and I'm just showing you one because all of these look pretty much the same. With all of these chemistries, we see no local ordering of titanium or vanadium. The same true with niobium with the other chemistries across the entire compositional range. So when we say it's a solid solution, it's truly a random arrangement of titanium and vanadium across these samples, or titanium, niobium, niobium, vanadium, right? So if we think back to the optical properties, what we actually see, give me one second. So what we actually see is that we can visually see that the MXene colloidal dispersions are changing in color. So we have vanadium here that we can see the gradual shift between these by eye. You could see the same thing happening with titanium niobium. And again, you can't see this with the vanadium niobium because it's the plasmon resonance is over near the IR. Now, one of the things we saw, which was very interesting, is instead of it being a single plasmon resonance that was related to only one chemistry, I was initially expecting that we would have some plasmon resonance that just shifts in between, and we can essentially choose what our plasmon resonance would be in between. But what we saw was actually more complicated. So we instead see two characteristic plasmon resonances. So I previously mentioned that the Ti2C1 is over here around 550. The niobium 2C1 is over around 1,000 or 1,100 nanometers. And so what we see here is quite interesting for two reasons. The first is if you look at where this plasmon resonance is, it's actually shifting. So we see a gradual shift in where the plasmon resonance is, in addition to the double plasmon resonance we see. Now, what this means is not only are we getting optical properties that you can't get otherwise with any other MXene chemistry, but we know that the electronic properties of the MXenes have to be affected by the other M elements on the MXene. So whichever M elements we're putting in have to necessarily lead to some kind of nonlinear effect or different effect. And this is important for a few reasons. If we're talking about application space, for example, within applications, if you want to use this as an electrochromic material, if I'm working with just pure Ti2C, for example, my plasmon resonance is at 550. And what Xuehang was showing is as you cycle it, you're changing its oxidation state. And so you can change its plasmon resonance with this as well. And if you're working with a pure MXene, you have some linear change in this. But if you have one of these solid solution MXenes with two plasmon resonances, both of these peaks will be changing in different ways than each other is. And so this leads to a nonlinear, kind of a double nonlinear property change that allows us to access MXene properties that we can't get otherwise. So one other application that I find to be incredibly interesting and incredibly useful is the electronic properties themselves. So Xuehang mentioned that MXenes are generally very conductive. We see up to about 20,000 Siemens per centimeter conductivity for Ti3C2. So Ti2C is actually the second most conductive MXene, where we can see a conductivity of around 5,000 Siemens per centimeter. But niobium 2C is historically known as one of the least conductive MXenes, with a conductivity around 20 Siemens per centimeter. And so if we look at just this R versus T diagram of just this one solid solution MXene, we can actually change the electrical conductivity over 7 orders of magnitude with just this one MXene series. And this gives us an absolutely huge range of properties that are just available to us. And if you look, it's exactly correlated with the chemistry. So I can essentially choose whatever electrical conductivity I want with MXenes, and then design the chemistry based on that. If I have this as my calibration curve, I can say if I want a MXene anywhere with an electrical conductivity in between them, I can then calculate what the chemistry should be and go and make it in lab, and then a week later have this new MXene that is perfectly tailored towards my electrical applications. And the same is true with titanium, vanadium, and vanadium niobium. We can essentially choose the MXene chemistry, and so we can start targeting these kind of arrays of properties we want. If we want to target specific optical properties mixed with specific electrical properties, we can choose a chemistry based on this. We don't have to essentially just use whatever is available. We can start designing custom-made MXenes, so custom chemistries for the specific application to make it the best it could be instead of just what is available. Now, I mentioned before that a lot of stuff affects MXenes. There's many variables that can affect MXenes. And so we were very interested just to confirm with one MXene series, so the titanium niobium series, that if we change a couple of the primary variables in MXenes, so the titanium to niobium content, the flake size, or the D spacing, so the interlayer spacing, which of these is going to affect our properties most, which is going to be most correlated? And so this is our Hall coefficient, the resistivity at 300 Kelvin, at 10 Kelvin, and the ratio of resistivities. And what we see is in almost every case, with the exception of this ratio of resistivities, the M-site chemistry has the highest correlation with what we see in differences of properties. And so, of course, there is some other correlation with these, but primarily the primary driving factor for the change in these properties is the M-site chemistry. Even if we have different flake sizes, even if we have different intercalants, even if we have different amounts of defects, changing the M-site chemistry is our first big gate to choosing our properties. And so I know we don't have an infinite amount of time in this lecture, and so we're not going to try to go through the entire density of states, but there's a few things I want to draw your attention to. So in this, if you look at the titanium D band, so this reddish orange color, and we just qualitatively look at what the structure looks like, right? You can see that there's kind of this double shoulder, but it starts to change. And we start getting different calculated electronic structures based on whatever our M-site chemistry is. So this is leading to a change in the electronic properties of both titanium and niobium in this case, in a way that we can't really access otherwise. Now, I was a bit surprised. So the titanium branching ratio is essentially the number of free electrons per titanium. And what this is telling us is even among different chemistries, we have different relationships. I was expecting both of these to be roughly linear, but what we see is a roughly linear trend with the titanium vanadium samples, but we don't see that same kind of nice trend with titanium niobium. And so what this means is we're not seeing the same linear or nonlinear changes in properties, but it depends again on the specific M-site chemistries that we're putting together. So we can start to access or target emergent properties that you can't get with other MXene chemistries by studying these fundamental parameters. So this allows us to access, for example, titanium oxidation states that you can't get with other M-site chemistries, with pure Ms, or even with other mixed solid solution MXenes. So this is something that is, I think, incredibly exciting. And so just to confirm this result, we did an EEL study where we were looking at the L3 to L2 edge, and we see the same kind of trends we were looking at. So we see the same linear trend in the titanium ratio, whereas with vanadium, again, we don't see that same kind of nice trend. So if you're interested, we looked at a number of other chemistries in this article where we were looking at these different branching ratios to understand this. And so what this tells me is that the MXene chemistries, the relationship that we see between MXene chemistry and their properties is quite a bit more complicated than we initially imagined, but that's a good thing. That means we can start to target properties, we can start to target systems that we may not even understand yet by studying these fundamental properties. So I will show you two quick examples, then I will briefly talk about a few other things. So one really nice application of solid solution MXenes is using them for electromagnetic interference shielding, so EMI shielding. So if you look at this diagram, so we know that there's generally a correlation between the conductivity of MXenes and their EMI shielding efficiency. And so this holds true of almost every this holds true of every MXene chemistry, from the least conductive to the most conductive MXenes. And so this depends on synthesis conditions, it depends on a lot of stuff, but the trend holds true. And again, the problem that we run into is if we want to choose a specific EMI shielding efficiency, if we want to choose a specific reflectivity or absorption, you can start tailoring your MXenes to start targeting this. So we know in the titanium niobium system or the vanadium niobium system that you can choose what you want your conductivity to be, and we see the same trend in EMI shielding with conductivity. So we can start choosing the properties we want in EMI shielding, for example, or we can do the same thing in solid solution MXenes for electrochemical energy storage. So we looked at two of these series of MXenes, so from Ti2C to niobium 2C. And generally, if you look, you can see that there is a relationship as it goes from one extreme to the other. It takes on more niobium characteristics as it goes this way. You can see the titanium characteristics of these redox peaks becoming more visible, more pertinent as you move to the higher titanium. And the same is going to be true with the vanadium niobium as well. Now, what this means is we can choose what we want our electrochemical energy storage CVs to look like. And what I found to be very exciting as well is in a lot of these cases, we actually saw that the highest capacitance was not in the edge cases. So it was not in niobium 2C, Ti2C, or V2C, but it actually happened to be in one of these intermediate middle compositions. So this vanadium 1.2, niobium 0.8 outperformed all others in terms of its energy storage in the niobium vanadium series. And we see the same thing in some cases in the titanium 1.6, niobium 0.4. And so this is exciting. So we know that the M-site chemistry affects the electronic state, and so it in turn affects the electrochemical energy storage. And I'm only showing CVs and capacitance, but this same trend holds true with the life cycle of these electrochemical energy storage cells as well. So it's well known that Ti2C is one of the lesser stable MXenes, whereas niobium 2C is incredibly stable. And so just doping in this small amount of niobium makes this one chemistry that has nearly the highest capacitance in all cases, and it increases its life cycle or its lifetime by an order of magnitude. So we get to then start playing and optimizing these different variables to start choosing applications and properties of interest that are best tailored towards what we're trying to do. I'm just going to briefly mention, because I know I'm running late on time, using mixed M chemistries, we're able to stabilize a number of different structures. So as of now, we've discovered 3 M5X4 MXenes, and all 3 of them are solid solutions. This is a molybdenum vanadium solid solution. We have a titanium tantalum solid solution and a titanium niobium solid solution that are stable. And what's very interesting is they're only stable under very specific chemistries. So that's why you'll see this, is if you deviate from this, you end up getting mixtures of max phases and not phase pure materials. So this article came out quite literally 2 or 3 weeks ago. So if you're interested in those, feel free to check them out. And the reason this is also very exciting is it allows us to access properties we can't get otherwise. So this MO4VC4 MXene is stable up to about 1,000 degrees Celsius, which is incredible for a 2-dimensional material. And we know that the electrical conductivity isn't severely affected by having organic intercalants that are heavily electron withdrawing on the surface because of the thickness. I was also excited to see that there's no characteristic plasmon resonance with these. So as you get to these thicker MXenes, it seems like you get essentially a dull gray, completely transparent MXene. And so you can imagine if you're making solar cells. So if you're working with lead halide perovskites, for example, if you would spray coat a monolayer of MXenes down, you can protect them from degradation with humidity while not drastically reducing its quantum efficiency. So that's why it's very important to study these different chemistries and different structures. Now, this paper just came out about a week ago. And I do want to stress, I focused on M site variation, but you can do the same thing with X site variation. So you can do the same thing with carbonitrides across many different structures. So we, as a demonstration, showed Ti2, aluminum carbonitride, and then the corresponding MXene, Ti3 and Ti4. And it allows us to do the same kind of trick where we choose what our carbon to nitrogen ratio is, and we begin to study the properties. So this is an early study that we published in JACS, and we show that, for example, the thermal stability of the titanium carbonitrides depends on the carbon to nitrogen ratio because of the different bonding motifs that you have in carbonitrides. And the very last thing I just want to stress is, even though I was talking about carbon to nitrogen, we've recently seen that you could have oxygen in your X site as well. And so depending on how you produce or purchase your max phase, that will carry over to your MXenes. And we see in some cases we can get nearly oxygen-free MXenes, whereas a lot of commercial max phases or max phases produced in less than ideal conditions will lead to a huge amount of oxygen in the carbon sublattice. So this is one of the reasons why you will see people talk about stability that can be on the order of years versus on the order of weeks. And so the conductivity of this is around 20,000 Siemens per centimeter, and this is around 2,000. So it's important to note and just keep that in mind. And so I want to stress very much solid solution MXenes, multiple M chemistries, multiple X chemistries allow us to target new and exciting properties that we may not have experienced otherwise. This is a, I think, comprehensive list of all of the current MXene chemistries that exist. Actually, it can't be comprehensive because this list came out before our carbonitride paper, so sorry about that. And I just want to thank all of my collaborators, Drexel Nanomaterials Institute, where most of this work was done, Yuri Gagotsi, all of our funding agencies. And I would like to thank you all very much for taking the time to listen to me. And I'm excited for our panel discussion at the end.
Thank you so much, Christopher. Thank you so much for your talk. And you gave me a very deep understanding of chemistry and the properties of the MXenes. Okay, let's move on to our next speaker, the Professor Shayan Seyedin. Yeah, let me first introduce the Shayan Seyedin. So, Professor. Oh, okay. Professor Shayan Seyedin is a senior lecturer, which is equals to associate professor in digital material manufacturing at Newcastle University, UK. He previously worked at Molecular Science Research Hub, Imperial College London. He was awarded a PhD in chemistry from the University of Rutgers in 2014. In 2017, he received the Alfred Deakin Postdoc Research Fellow for his research at Deakin University, Australia. He was then awarded the Endeavour Research Fellowship to work at the USA Rutgers University. His research focusing on processing 2D nanomaterials like graphene or MXene into neat hybrid and composite structures, such as film, fibers, jars, and textiles that could be store energy or sense strain, pressure, or touch. So far, he has published more than 50 journal articles and book chapters. His work has received more than 4,500 citations, with an H index of 33, and he has been featured in 9 journals cover page, 5 radio interviews, and more than 50 media outlets. Okay, let's welcome Shayan Seyedin. That's your time.
All right, thank you so much for the introduction. I'm going to talk about MXene fibers for wearable applications. In the last few decades, we saw a paradigm shift from desktop computers to portable devices such as laptops and mobile phones. So these are essentially integrated in our daily lives. And now we want to essentially go towards devices that are wearable, so things like smartwatches and Fitbit and so on. But one of the problems that these devices have, they're still bulky, they use traditional electronics, and my research essentially focuses on making these devices textile-based, so that they can be worn they can be worn like everyday clothes. This research essentially cannot be done using conventional materials because things like metals and traditional semiconductors are typically not inherently compatible with textile-based structures. So that requires essentially a new types of devices that are fiber-based so that they can be integrated in clothes. And having devices that can operate at the textile level then enables us to do things that are not currently possible using conventional portable and wearable devices. So for example, we can have textiles that can be worn and sense our body movement, and our clothes can essentially store energy from movement of our body, and these could enable new types of applications such as body movement monitoring and sports rehabilitation and things that are not currently possible. As I mentioned, we need to look at new materials and we need to redesign how we make electronic devices. So one of the materials that are promising for fiber-based applications is MXenes. So I'm sure we've heard a lot about MXenes, and I'm not going to talk about what they are because that's been sufficiently covered. But generally, MXenes are transition metal carbides or nitrides that are derived from precursor materials commonly known as MXphase. So the reason why they are suitable for fiber-based application is just because they offer a wide range of electrical properties, as was previously discussed, and in cases the electrical conductivity can go up to 15,000 Siemens per centimeter, for example, for Ti3C2. And not only that, they also offer additional properties like energy storage property, things that are not offered by metallic conductors, and that is essentially shown by the high volumetric capacitance in the order of 1,500 farad per cubic centimeter for Ti3C2. And the other property that MXenes offer is essentially the ability to disperse in a wide range of solvents. So here, for example, you see one sheet of MXene that is observed under transmission electron microscopy, and here is essentially the X-ray diffraction pattern showing the completely removal of aluminium layer in Ti3 AlC2 max phase and the downshift of 002 peak, which is essentially, what is referred to as complete etching. But typically, if you follow this process, the etching process, you end up with MXene dispersion in water, which can be processed using conventional processing techniques like solution-based processing. But for a lot of applications, we need MXene in a wide range of polar solvents or organic solvents, things like ethanol, IPA, acetone, DMF, and DMSO, and that are commonly used, for fiber processing. And that was essentially the first thing that we did. We looked at the dispersibility of MXene in a wide range of solvent, and we found that MXene can be dispersed in a range of polar organic solvents using solvent exchange. And one of the common issues that MXenes might have is the degradation, and using this organic solvent processing, the degradation of MXene could also be mitigated to some extent. So, for example, here is a Ti3C2 sheet of MXene, and that is observed under TEM after 28 days, and you can still see the sheet-like structure is maintained, and you can see the presence of titanium and carbon without any noticeable degradation. So that is promising for fiber-based application, because we can now achieve MXene for a wide, in a wide range of solvents that is stable, which is essentially the essential prerequisite for fiber processing. So the first thing that we did was essentially we took MXene, Ti3C2 MXene, and coated it on carbon fiber substrates and prepared electrodes, and then used two of these electrodes and assembled those in a yarn-shaped supercapacitor device by using a gel-like gel-based electrolyte. And then we looked at the energy storage performance of this yarn-shaped supercapacitor, and looking at the cyclic voltammetry, we saw that in voltage range of 0 to 0.5, it behaved like a capacitive system. And then looking at charge discharge, and we saw that by charging this device to 0.5 volts, we could take charge storage that could be released over a short period of time. And that is essentially a symmetric type shape, which is typically seen in capacitive systems. And then looking at the value of capacitance, we were able to get a capacitance of up to 132 millifarads per centimeter. And that allowed us to essentially assemble a yarn-shaped device by pairing 3 of these supercapacitor devices to achieve a 1.5 volts that could essentially turn on a lab timer. However, we wanted to make fibers directly from MXene, so we started focusing on solution-based processing in a way that we get fibers, individual fibers from MXene. Initially, our attempt in order to make pure MXene fibers did not succeed, but at the time we knew how to make graphene oxide fiber, so we decided to make MXene graphene oxide hybrid fibers. If you look at graphene oxide dispersions, you can at high concentration you can see birefringence, essentially, textures like this, and that is indicative of presence of liquid crystal domains. It turned out that these liquid crystal behaviors are desirable for fiber-based application, and we can use a technique called wet spinning to make those dispersions into graphene oxide fibers. So I prepared a video that shows exactly what happens during this wet spinning process. So essentially you have a solution or dispersion that is injected into a coagulation bath. So this can be a non-solvent or can be a cross-linking agent. And as a result of solvent-non-solvent interaction or chemical reactions, then the jet of the solution or formulation solidifies, and then you can collect it continuously on a winder. And using this technique, I was able to produce graphene oxide MXene hybrid fibers that contained up to 88% weight of MXene. So if you look at these fibers under a scanning electron microscope, you see that the large graphene sheets are essentially acting as essentially can hold these smaller MXene sheets together, and here essentially we end up with a compact fibers that offers some degree of flexibility, so it can be essentially knotted like this as well. Looking at the mechanical properties, essentially adding MXene resulted in some a small improvement in mechanical properties such as Young's modulus and tensile strength. So we were able to get a tensile strength of up to 150 megapascals using MXene graphene oxide fibers. But at high loadings, like loadings beyond 50%, we started getting a decrease in strain at break. But the conductivity increased significantly from about 30 Siemens per centimeter to somewhere about 80 Siemens per centimeter. And using these MXene graphene oxide hybrid fibers, then we were able to get fiber-based supercapacitors. So looking at the CV, you see that for this is for RGO, and by increasing the MXene, the area under the curve gradually increases, and that essentially translates to increase in capacitance or a specific capacitance. So looking at the volumetric capacitance with respect to MXene content, you see that at 88% MXene, we can get a specific capacitance of up to 341 farads per cubic centimeter. And looking at charge discharge, we also see a reasonably symmetric behavior. And at the current density of 0.5 amps per gram, we could get the highest charge storage time. And we've also looked at the cyclability of these fiber electrodes, and we found that these fibers were stable up to 20,000 cycles without any loss in performance. So looking at the Coulombic efficiency, you see almost 100% Coulombic efficiency, and with virtually no degradation of capacitance over such a long cyclic time cycles. while this was encouraging, looking at the potential window, we were operating at the range of 0 to 0.8 volts, which is not an ideal potential window for MXene. And that's because looking at the SEM, you see that the large graphene oxide sheets essentially wrap around the smaller MXene sheets, and that prevents us to fully access the energy storage property of MXene. So then we decided to move towards other types of matrices, and we use PEDOT-PSS as opposed to graphene oxide to make hybrid fibers. So at the time we knew how to make PEDOT-PSS fibers using the same vector spinning process by essentially using sulfuric acid as a coagulation mat. And then we prepared hybrid formulations of MXene and PEDOT-PSS and followed the same process, and we were able to incorporate up to 78% MXene into PEDOT-PSS fiber with a conductivity that was up to 3,800 Siemens per centimeter. So here, essentially, if you look at the cross-section of the fiber, you see that the MXene sheets are essentially in contact, and they are surrounded by PEDOT-PSS, smaller PEDOT-PSS chains, and looking at essentially titanium and looking at EDX, you see the presence of titanium and sulfur, which is essentially indicative of the presence of MXene and PEDOT-PSS. And this time, using cyclic voltammetry, we were able to get a voltage or potential window of -0.7 to 0.2 volts, which is essentially the same operation window of MXene. This resulted in a high specific capacitance of 615 farads per cubic centimeter, which is almost twice what we used to get with graphene oxide MXene. And the fibers were flexible as well, so they could form knots like this. And one cool thing that they allowed us to do was essentially, we could wrap them around an elastic yarn, which is essentially silicon rubber yarn. And then we were able to make elastic fiber supercapacitors. But we were limited to 78% of MXene, so this was the highest that we could load to the fiber that enables spinability. So we then moved to using another technique, which is called bias scrolling. So here we essentially used the carbon nanotube carbon nanotube sheet as our substrate, and then we deposited MXene, which is essentially titanium carbide Ti3C2 dispersion onto this, and then by rolling these carbon nanotube sheets, then we ended up with yarns that could contain up to 97.48% MXene. So essentially fibers that are predominantly made of MXene. So looking at SEM, so you see that these are essentially, carbon nanotube sheets that are rolled, and they hold all MXene sheets. So this is essentially carbon nanotube that is acting as a matrix for smaller MXene sheets. And then looking at cyclic voltammetry, we were still able to operate in the same potential window of MXene, and this time with a much improved specific capacitance. So we were able to get a capacitance of over 1,000 farads per cubic centimeter. And looking at charge discharge, you still see a reasonably symmetric charge-discharge behavior. But if you look at the cyclic voltammetry, here we are limited to approximately 0.7 volts, which is not really sufficient for powering electronic devices. So mostly we need at least 1.5 volts to be able to turn on, small electronic devices. And that was our motivation to essentially go towards asymmetric devices. So we used the same technique, which is essentially bias scrolling technique. And this time we used ruthenium dioxide and made ruthenium dioxide carbon nanotube fibers. And using ruthenium dioxide carbon nanotube fibers as positive electrode and MXene as a negative electrode, then we were able to make an asymmetric supercapacitor device that could deliver a voltage of up to 1.6 volts. So here, essentially, if you look at the CV, you see that it runs from 0 to approximately 1.6 volts. And the behavior is reasonably rectangular, the shape of the CV curve, and looking at the device performance, we were able to get a high energy density of almost 62 milliwatt hour per centimeter cubed, and high power density of over 5,000 milliwatts hour per centimeter cubed. And then we took this asymmetric device and integrated into a piece of fabric. And then this fabric, we showed that this fabric could actually turn on an LED and a digital watch and also a lab timer. So essentially, we this time we charged these fibers and then connected it to an LED or digital watch or a timer. And the energy stored within these yarns or fibers could turn on a number of different electronic devices like LED, digital watch, and timers. We've also made pressure sensor yarns and textiles using MXene. So here we essentially coated coated cotton yarns with a small and large MXenes, and we ended up with fibers that had or yarns that had MXene loading of up to 77%. And looking at these yarns during the washing cycles, we observed that we could actually wash them many times at even high temperature, 80 degrees Celsius, without noticeable change in the electrical properties or MXene loading. So that essentially is promising, because that is then then allows us to make devices of textile-based devices that can be washed. Then we made these yarns into fabrics and took two pieces of these fabrics and sandwiched a dielectric layer and made a pressure sensor out of it. So here is essentially a piece of fabric made of MXene yarns that is acting as a pressure sensor. So when we press this patch, we get an increase in capacitance, and that's how essentially we can sense pressure. So looking at the change in capacitance, with respect to a strain, we see that by increasing the strain, the capacitance increases with a gauge factor of 6, which is reasonably high. And surprisingly, there's almost no drift in the sensing signal. We've also made composite fibers using MXene. We used the same wet spinning technique and incorporated MXene into polyurethane. And we previously used the same approach in order to integrate a number of other conductive fillers within polyurethane, including PSS, carbon black, carbon nanotube, and liquid phase exfoliation graphene, and liquid crystal graphene oxide. So essentially, this is polyurethane MXene fiber. And here we can essentially achieve a high loading, so we can make up to fibers that go from 0% MXene up to 100% MXene. So looking at the electrical conductivity, you see a reasonably low percolation threshold, which is about 1/8%. And the conductivity can go to as high as 1,000 Siemens per centimeter, which is much higher than other types of fibers that we produced before, including polyurethane PSS and polyurethane graphene. And also, we were able to get the highest Young's modulus or stiffness with polyurethane MXene as opposed to other yarns, other fibers. And we also moved towards making coaxial fibers. So we essentially made fibers that have polyurethane core and MXene polyurethane sheath. And because these fibers are conductive and are highly stretchable, then they could act as strain sensors. So if you stretch these fibers, the resistance goes up, and that's essentially how you can sense strain. So, for example, here you see the behavior of different fibers at different MXene composition. And you can get fibers that can sense up to 150%. So then we made, knitted patches out of these fibers, and we showed that we can actually monitor body movement. So essentially, by wearing these knitted textiles, we can sense the movement of our body. So here, for example, this patch is worn on a knee of a volunteer, and as you bend the knee, the voltage or resistance goes up, and when you release it, the resistance goes down, and that's essentially how you can sense your body movement. And we showed that this process is scalable, so you can use a pilot scale wet spinning setup and make a spool that contains over 1,000 meters of these fibers. And we can also make them multi-filament, which is essentially what is used in everyday textile. And we can actually make these in a wide range of different patterns, like plain, conate, and with different loop patterns. And similarly, we can actually wear it on different parts of body and use that for real-time body movement monitoring. So here, essentially, we have a wireless transmitter that is connected to this patch of fabric and transmits the signal to a personal computer. And looking at the signal, you can see that it changes with respect to the bending movement. And it also responds to very fast movements of the limb as well. One issue that we observed with this approach for composite fibers was essentially the non-linear behavior of sensing. So if you look at this behavior, so the sensing is not very linear, and also there is some drift in the sensing signal. Then we move towards another approach, which is called electrospinning, and then we use a modified version of that, which is essentially, bat electrospinning. So essentially, doing the electrospinning process in conjunction with wet spinning process, and using that, we were able to get cool structures like these that are essentially, nanofibers with, MXene integrated inside the individual nanofibers. So using this technique, we were able to get a very high conductivity up to 1200 Siemens per centimeter. And we showed that this technique can be applied to both hydrophilic yarns or polymers like nylon, and also hydrophobic polymers like polyurethane. And then using these polyurethane MXene fibers, we observed that when we use them as strain sensors, we actually get a very consistent sensing signal, meaning that the drift is reasonably low. So looking at this resistance change with respect to strain, then you see that as we increase the strain, and the resistance increases almost linearly, and every time when we stretch the fiber, resistance gets back to the original condition. So that is indicative of low drift, with a gauge factor which is very high, so over 1700, which indicates essentially the high sensitivity of these yarns. So I'm conscious of the time, but the last thing that I want to talk about is essentially, this is one of our recent achievements, which is essentially, the discovery of the liquid crystal phase in MXene. Liquid crystal are essentially ordered phases that allow us to produce ordered structures, and these are highly desirable for a lot of applications, for example, for fiber-based applications, because then they allow us to produce fibers that have high orientation and have high mechanical properties. Looking at large MXene sheets, we observe that we can get a liquid crystal, pneumatic liquid crystal phase at a concentration of about 13.2 milligrams per milliliter. And this typically happens at a concentration of about 66 milligrams per milliliter for a small MXene sheets. And looking at the behavior of that is suggested by the theory, Onsager theory, then this essentially shows us that as the particle size, or as the sheet size increases, then this transition to LC phase occurs at reasonably low concentration. So this is ideal because then, liquid crystal formation is desirable for fiber spinning, and that means that we can achieve fibers at low concentration. We also observed pneumatic phases in a wide range of organic solvents such as DMF, DMSO, and NMP. And later on, we also showed that other MXenes such as MO2, TI2C3, and TI2C are also form liquid crystal phases in solution. And using the same wet spinning setup, we were indeed able to make pure fibers out of MXene. So this is essentially a spool of titanium Ti3C2 fiber that is collected on a spool. And these fibers showed a high conductivity of over 7,000 Siemens per centimeter. We could also produce other types of fibers out of other MXenes, such as MO2, Ti2C3. And then when used as supercapacitor, they resulted in a high specific capacitance of 1265 farads per centimeter cube, which is close to the close to the performance that has been reported for other MXene-based structures, such as MXene films. So, in summary,
you have 2 minutes left. Okay.
Yes. Thank you. So in summary, I showed you that we can use a wide range of fabrication techniques such as coating, wet spinning, and bioscrolling to make fibers, yarns, and textiles based on MXene with a composition that ranges from neat fibers to hybrid composite fibers, and we can also make coaxial fibers. And the application of these fibers can be wide-ranging. You can use it for energy storage, strain sensing, pressure sensing, and even heating applications. Essentially, these works that I've shown are the result of collaboration and working with the students and researchers in multiple different universities and institutions. And some of these works have also been featured in cover pages of different journals. And thank you so much for your attention.
Thank you so much. Thank you, Professor Seyedin. It was a very nice talk about the MXene-based wearable sensors. It's really nice. So I think we can move on to the panel discussion. And let me share the screen.
Okay. Yeah, Dr. Du, maybe I go first to ask the questions.
Okay, no problem.
Yeah. Okay, great. Yeah, actually, I'm doing some work for the wearable devices, so I'm very interested in science work. Yeah, so you give a few examples of vaccine, application for wearables. I saw you in the slides you have a demonstration for the washable, high temperature is also very stable, right? Yeah. So I'm wondering whether you try the low temperature or what's the reason behind why so?
So we tried a range of different temperatures from room temperature to 80 degrees. And I think we tried many different cycles, up to 10 cycles, I believe. And the fibers showed essentially no change in conductivity. And that's so probably one of the reasons why we saw, reasonably a stable performance was essentially, the integration of MXene within the yarn. Because we used a small MXene sheets, essentially they're wrapped around individual cotton fibers, and then we coated that with a large MXene sheet dispersion, which essentially had two different levels of coating, at fiber level coating and yarn level coating. We didn't see any MXene flaking off from the surface because of the high interactions of MXene sheets with the fibers of cotton.
Okay, great. I have another question is for the strain sensors. I see your strain sensors is quite simple, Yeah, just embodied, no kind of different shape, Yeah, no sensitivity is high. Because I'm a kind of person devices sensors. Normally, the structure design is important for the sensitivity. They'll give me some ideas for this strain sensors, very simple structures or you design structure.
So there are a wide range of properties that are important for a strain sensing application. One of them is sensing range. So how much can you stretch the fibers and they can sense? So for example, it's shown that in normal day activity, the textile can be stretched as much as 55%. So if a strain sensor can cover this range, that indicates that they are typically suitable for a wearable application. So that's the sensing range. So we need to make sure that the fibers that we produce or textiles that we produce are capable of sensing high strains that are large enough beyond 55%. And also they are sensitive. So sensitivity, which is essentially defined by gauge factor, is essentially the magnitude of change of electrical signal, which could be resistance or capacitance or any other things like voltage, with respect to the amount of strain. So if a sensor has high gauge factor, then that means that it produces a lot of change in electrical property, resistance, capacitance, etc., with respect to the stretching or bending the formation. And that's typically ideal because we want to have a highly sensitive device that responds quite well to a stretching the formation. And also, there's another factor called drift. So we want to make sure that there's a consistent performance at different cycles. So when we stretch the textile, the resistance goes up or down, but then returns to the original value, and there's no drift, meaning that the resistance doesn't change with respect to time or with respect to cycle, because then that makes the sensitivity very complicated. So we want a stable, highly sensitive sensors that can cover a wide range of stretching and bending the formation.
Okay, great. Maybe I ask the questions about other speakers.
Yeah, I have a question for Xuehang. Xuehang, are you here? Yeah.
Yeah.
Could you share your ideas or opinions about the batteries or supercapacitors? These two are very hot topic in the last decade. Maybe you can share some of your opinions. Okay.
Opinions about choosing a battery or choosing a supercapacitor, or because
in the future, maybe which one can be domesticated in the market?
Yeah, it's thank you for the question. It's a tricky one because I work with a supercapacitor mostly. So of course, I would hope that supercapacitor can be market dominating, more market dominating in the future. However, so far, because compared to the battery, the supercapacitor have relatively lower energy. So far, it's a little bit difficult really to compete with the other batteries, especially if we are competing with the lithium-ion or lithium metal batteries. Yeah, so the limitation on the energy storage so far is really the problem for supercapacitor. Meanwhile, if there are more applications on the high rate operations, high power devices, then the supercapacitor can find its more application in the future. And also, as what the Shayan is doing, so a supercapacitor can really find applications in wearable devices in the interdigitated micro supercapacitors. But those are some applications that's waiting to be more broadly extended. So if these directions can further grow, it also will further extend the application of supercapacitors.
Yeah. And I was wondering, do you know the limitation of the supercapacitors in the MXene-based material? Does the MXene material have a theoretical capacitance in the supercapacitors. Yeah, so there's a limitation. And what we can do in the future to improve the performance of the MXene-based material in supercapacitors.
Yeah, it's a very good question. For like the limitation of a double layer capacitor or pseudocapacitors. Like for double layer capacitors, highly depend on, for example, the surface area, the pole side distribution, and also the ion distance or something like that to determine how large per surface area the capacitor can store. But for the pseudocapacitor, the capacitance is determined by two parts. So one part is contributed by the double layer capacitance, another part is contributed by the surface redox or intercalation redox. So those parts, the pseudocapacitance contribution to the pseudocapacitor or MXene-based pseudocapacitor should be more dominant compared to the double layer contribution. So then let's extend a little bit on like the limitation of the pseudocapacitance of MXene. So so far the redox charge storage capacity of a material is depend on like the electron transfer per transition metal that can deliver for the material. So for example, for TiO2 in acidic electrolytes, per titanium, the electron transfer is about I think it's less than 0.2 electron. So if we are able to increase the electron transfer per titanium, then we are able to increase the overall capacitance that is contributed by the surface redox. However, in order to increase this number, then we need to enable reversible valence change of titanium. Yeah, because you know that now the valence of titanium is about 2.4, 2.5-ish. However, if we oxidize it into titanium 4+, then this process is irreversible. So it means that if we oxidize MXene to titanium oxide, this one can never be back anymore. So then it means that if we really want to improve the pseudocapacitance of MXene, we need to find the maximum reversible valence of the transition metal. So it's also also highly depend on because I mentioned about titanium, but also Chris is working with many different type of MXene. So it's also possible that in other MXene choices, like for example vanadium, they can have more valence change and they can have like more reversible valence change. Then we are able to get even higher pseudocapacitance.
Yeah. Thank you so much for your suggestions. I think Professor Shuck may very know that because he can prepare a lot of different MXenes. Yeah, can provide some potentials in the high performance supercapacitors. Okay, I have another question for Professor Shuck, and I say you can prepare the kilogram batch size of MXene, right? And what's the difference in synthesis of kilogram MXene and gram batch size MXene?
Yeah,
can we prepare in our lab?
Well, so this is a very, very good question, and it's a very important question. So whenever you're synthesizing MXenes, in any case, it's a volume-based synthesis. So if I'm producing, I could produce kilos of max phase easy. That's standard powder metallurgy. But the synthesis of MXenes is a top-down approach. So it does not have an area-based limitation. So what this means is if you take whatever reactor vessel and you scale it up. So if you take a 100 milliliter vessel, you scale it up to 1 liter. You can effectively synthesize 10 times more MXene. The only limitation we run into is necessarily heat transfer in this case. And the MXene etching reaction isn't exothermic necessarily. So this isn't an issue we run into. So we can scale up essentially as long as you have a reactor vessel that is HF compatible and you have something that can effectively stir or agitate the entire volume based, you can scale up to a kilo like we did in our lab, or even larger amounts, without any loss, change, or different properties.
Oh, this is amazing. Thank you. Thank you.
John, maybe I follow this question for Christopher. So you
Yeah,
get
yeah,
this
sure.
you get this mass production, for the MXenes. So is the price or the cost that could be, get very low?
Yeah. So if we think about generally the cost of MXene, the two most expensive things are the cost of the transition metal precursor, or actually three things: cost of a transition metal precursor, the cost of energy to produce the max phase, and then the manual labor cost. And the manual labor cost in the laboratory scale synthesis is about 100 times more expensive than the precursor or energy costs. So if I produce 10 grams, I basically cut the cost of MXene down to 10%. And so if we want to do large scale synthesis and commercialization of MXenes, we can asymptotically approach the price of a precursor. As we do larger batch sizes, we remove manual manipulation steps. So, as much as I enjoy doing hours of centrifugation by hand, you can automate this process. You can do some clever chemical engineering to get rid of it. Likewise, all of the different steps of the MXene production process can be automated, can be scaled up, and you can essentially have any industrial chemical engineer produce kilos, tens of kilos, hundreds of kilos with little manual input, making the cost incredibly low.
Yeah, that's good. I think that's the right way for MXene to popular materials, in the future. Yeah, as Christopher, you give a very nice talk about the carbide, MXenes. So I'm especially you can make that transparent or something. Yeah, I have a question. You have such a magic material, right? Yeah, you have magic finger to make that. Did you make some magic devices?
So I personally, I focus mostly on synthesis and hand off the MXenes to experts like Xuehang and Shayan, who can make devices much better than I can. So all of the stuff that I've shown, all of these applications can be used for essentially any application space. Not every different MXene will be best for those, because it depends very much on the specific application itself. I'll give you a good example. So niobium 2C, I mentioned, is not very conductive, around 20-25 Siemens per centimeter. So it's not going to be good for strain sensors or stress sensors, but it would be very good as a biomedicine agent for photothermal therapy because it absorbs at the NIR2 wavelength and is biocompatible. So it's, it depends on the specific applications, and it depends on the specific targeted properties you're going for.
Okay, cool. Yeah, continue. Yeah, make much more kind of magic. Yeah, got you. I'm fine.
Okay, thank you. And I have another question for Professor Shayan Seyedin. Yeah, you do really very interesting device using MXene material. And I was wondering if this sensor or device has some health effect on our skin.
Well, that's a very good question. So we didn't really study the hazardous nature of these fibers, but looking at the materials that we have, currently there's no, there's no toxicity reported for MXene. And some of the MXene electrodes are being used for bio applications like brain electrodes. So we are not dealing with toxic materials. And specifically, I guess for most of these fibers, the material that we are using as hosts, such as polyurethane, they're biocompatible materials, and they are used in everyday textile applications, like spandex is made of polyurethane. So They are widely used for everyday textiles as well. And the process that we are using, things like electrospinning, are industrially viable processes. So things like acrylic fibers are made using using wet spinning process in industrial scale. And some solvents that we use are essentially used in the production of acrylic, like dimethyl formamide and so on, and we use them for our sweaters and jumpers and so on. So these fibers, and so what I wanted to say is essentially the material is not hazardous. Manufacturing process that makes these fibers are not typically hazardous process, or doesn't lead to hazardous fibers. So then we don't really envisage issues related or health-related issues in terms of long-term wearing of these fibers.
Okay, thank you. And are these sensors washable? You mean when you made a jumper, maybe I want to put in the washing machine to wash it?
Well, probably, if we use devices like, if we encapsulate a supercapacitor device, for instance, then it would be possible to wash it. No one, electronics and washing.
Wash or washing machine first.
Yeah. So electronics and washing don't really go hand in hand. So you don't expect to put in your phone into a washing machine and
oh, no.
be okay. But probably one thing that could happen at fiber level is in encapsulating the device. For example, a supercapacitor device that forms like a cable-like structure and has an encapsulating layer that protects the supercapacitor device. But for things like sensors, for example, luckily, we are not using things like electrolyte that can leak out. So I expect that, for things like strain sensors and pressure sensors, we can achieve washability. There's nothing that prevents us from doing so. Because it's just a simple, piezo-resistive sensing on strain sensors, or capacitive sensing in pressure sensors. The only thing that we need to be conscious about is just use of conventional electronics. So if we are using, for example, wireless transmitters on a smart textile, then probably that could be taken off during the washing cycle, and that should help us with washability.
Okay, thank you. Thank you. Very interesting. Yeah, I think we can move to the next. And lastly, I want to issue the certification to our speakers. And thank you so much, Professor Xuehang Wang, for her talk revealing the charge storage process in titanium carbide MXene-based pseudocapacitors. And thank you, Professor Wang. And next, thank you so much, Professor Christopher Shuck. Thank you for your talk about using multiple elements to understand the chemistry and the structures of MXenes. Thank you so much, Professor Shuck. And we have the last speaker, Professor Shayan Seyedin. Thank you so much for your talk about the MXene fibers for wearable applications. That's very interesting. Thank you all our speakers. And I would like to introduce our next talk. Welcome to pay attention to our next talk, which is the lessons from molecular switches and machines, which will be held on October 24th. That is next Tuesday, and see you on next Tuesday. Have a nice day, guys. Yeah.
Bye. Very nice talk
Bye.
and a nice discussion.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我一样飞越最高山岗。I can，没有什么可以阻挡心中无限的力量。I can，你也能够像我